Alright, so section 6.9 is a short section at least, and it's on modeling, creating equations that kind of fit data, or at least more or less fit data. Each of the problems in 6.9 is a word problem. The problems start off with a short description and then some data that describes, or that the description decides. In this particular problem too, it says this data shows the cooling temperature of a car engine, and so like in 5-minute intervals from the second the car engine is shut off to 45 minutes, the temperature of the engine was taken. And these are completely made up numbers, so I don't know that they're realistic. I don't remember what car engines run at in terms of a temperature. But this table would say when you shut the car engine off, it was running at 240 degrees Fahrenheit. In 5 minutes, it went down to 220, then 202 at 10 minutes. 45 minutes, it was still 133 degrees. The first thing that the instructions say is plot the data using a graphing calculator. So just to refresh your memory on how to do that, and you won't have on the review and on the test, you won't have to plot the data, but just we need the data in there to come up with the equation that we're going to get later. So I'm going to hit my stat button, hit enter on edit, and I'm going to clear out my list 1 and list 2 by going to the top of the list and hitting clear. And I'm going to enter in list 1 the times in minutes, the 0, the 5, the 10 minutes, and so forth. And then in list 2, I'm going to enter the temperature of the engine, 240 degrees, 220 degrees, 202, 186. And so into my calculator, as we speak, in list 1 are the times, in list 2 are the temperatures, and I'm going to plot these. So I'm going to hit second and quit. I'm going to hit second and y equals to turn my stat plot on. Right now my plot 1 says off. I'm going to hit enter, and then instead of having the blacked out off, I'm going to have the blacked off on. So now my stat plot is on. So if I hit my y equals button now, let me clear the functions out that are in there. The plot 1 is blackened. If it's not blackened, you're not going to get the data graphed. Now to graph the data on my calculator, now that I've entered the data in these and I've set my stat plot on, I hit the zoom button and arrow down till I find zoom stat, and it'll set a window for me that's appropriate. So here's zoom stat, and the window it chose is different than the window I chose with my computer program, but it's probably a better window than I have. So this is plotting the data. When I look at this data, I have to decide what type of equation this would match this data, and it almost looks like a line would work. For the data for a line to work, the gap between each of the temperatures, which should be constant. So between the first 5 minutes, the temperature went down 20 degrees. The second 5 minutes, it went down 18 degrees, and then 16 degrees, and 14 degrees, and 13 degrees. Because the change in the temperature isn't constant, a line wouldn't really be appropriate. We graphed some functions earlier in this chapter, and this kind of looks like the graph of maybe 1/2 to the x power, and most of the data that we're going to graph, it's going to fit some sort of exponential function, a function that has an x in the exponent. As a matter of fact, you can see if you peek at part C of this question, I say, find the appropriate regression equation, and I tell you how I want the equation to look. These are the style of equations that we had in section 6.8. So I need to create an equation. I tell you I want you to create an equation like this, because as I'm moving from left to right, it's going downhill. When I get this equation, the k that we were solving for in the last section is going to be negative. So on my calculator, if I hit the stat button and go over to calc, the type of equation that my calculator calls this is exponential regression, EXPREG. So the type of model that's going to be appropriate, because the data looks like it's an exponential, the graph looks like it's exponential decay, I'm going to say that exponential regression is going to be the best model for this. And when I actually do the exponential regression, I'll see that the R's are really good numbers, bigger than 0.8, so the equation is going to be a reasonable fit. So I looked at the data, doing my zoom stat, even though, because it's kind of curving up like this, that's what exponential decay looks like. So this is going to be an exponential regression. I'm going to find an equation on my calculator. This is really depressing, well, almost depressing, but it's harder than it needs to be. My calculator, it's going to give me an equation, but the equation that my calculator gives me to map the data isn't in a really classically nice form. I don't know why the programmers of this calculator gave me the ability to do exponential regression, but didn't write it in the classic form. So the equation that my calculator is going to give me is in this form. Y equals A times B to the, I'll say t power, although the calculator will give x's, but the x's in my particular problem from the data represent the time in minutes. So the x, which I'm going to make t, is going to stand for time in minutes. And the y is going to stand for the temperature. So my calculator is going to give me an equation, but this equation isn't so nice. I'm going to need to transform this equation into the style of equation that I want it to be. And this is easy if I show you a shortcut, hard if I show you the right way to do it. So I'll show you the shortcut and the right way to do it, and you can decide what you want. So anyways, I'm going to come up with an equation, not in the nice form, but in a form that can be transformed to the nice form by hitting my stat button, going over to calculate, and going down to that option that says exponential regression. And when I do exponential regression on my calculator, I hit enter twice. It tells me that, first of all, it's a great fit, that the R is 0.97, the R squared is 0.98. That has to do with it being decay. It says this equation, y equals, and I'm just going to round everything to 3 decimals, y equals 231.384 times b to the x power, I'm going to make my xt to stand for time, times 0.986 to the t power can be used to make predictions about this data. This equation you can use to answer the questions that were asked. The question that was asked ultimately in part D is predict when the engine's temperature will be 140 degrees Fahrenheit. I could actually use this equation to do this, but it'd be doing you a disservice if I left the equation in this form. So what I'm going to do now is I'm going to transform the equation to the form P of t, that means maybe, well, P is going to be the temperature with respect to time, equals P sub 0 times e to the kt. In the formula, I need 2 amounts. I need a value for P sub 0 and a value for k. Even though P sub 0 is the initial temperature, I'm not going to use the initial 240 degrees. Somehow, this equation doesn't fit the data perfectly. It fits the data approximately well. I'm going to use the regression equation to make predictions, then I have to deal with its shortcomings. It doesn't go through the points perfectly, so the numbers that I get for the equation, they're not going to be perfect. What I'm going to need to do is I need to find a value for P sub 0 and I need to find a value for k. In my equation, I'm going to write P of t equals to something. Before the e, I'm going to write something for P sub 0, the initial temperature, which is really 240 degrees, but I'm going to get something slightly different when I use my calculator, when I use this equation, times kt. So I need a value to the left of the e for P sub 0 and to the left of the t for the k. And P0 is the easier one to get, even doing slickly. The correct way to get the P0, and it almost seems like it's an illegal correct way, is to use my equation, this equation, and set it equal to that equation. So what I'm going to do is take the equation that I have, y equals 231.384 times 0.986 to the t, and set it to the form that I want. I want P0 times e to the kt. What I'm about to do now seems like it should be completely illegal. For those of you that get high enough in math, you'll wind up doing this pretty frequently, but I don't think I've ever taught it to a lower class than this. So what I'm going to do to find the P0 is I'm going to let the t equal to 0. This equation has to be true for every value of t, so I'm going to let t equal to 0, and I'm going to go 231.384. This is not the shortcut method, this is the actual method, and I'll tell you how to shortcut it in a second. So I get this, 231.384 times 0.986 to the 0 equals P sub 0 times e to the k times 0. On the left-hand side, anything to the 0 power is 1, so I get 231.384 times 1. And on the right-hand side, I get P0 times e to the 0 power, because if I multiply the k times 0, I get 0. Left side's going to give me 231.384. Right side's going to give me P sub 0 times 1, because e to the 0 is 1. And this gives me P sub 0 equals, or the initial temperature according to the formula, is 231.384 degrees. So I've figured out a value for P sub 0. My P sub 0 is going to equal 231.384. It's always going to be the case when I'm transforming a TI 83 or 84 regression, exponential regression into a standard form, it's always going to be the case that the A from the formula, so my calculator gave me an A, the A, this 231 number, is going to be the P sub 0. So immediately when I go down the right my equation, the P sub 0 is the A from my calculator. It doesn't call it P sub 0, but it is that. I have room here, so I'm going to write P of t equals 231.384 times e, and I need to get something to the left of the t. So I'm partially done. So what my calculator gives me, this A is the P0 that I need for my formula. It doesn't call it the initial temperature, doesn't call it P sub 0, but that's what it is. The next thing I need to do is get a value for the K, and that's not as easy. The shortcut way to get the value for the K is just to take the natural log of the B. So let me do that real quickly, then I'll show you how to get it. So this is the cheating way, or the shortcut way. So the shortcut way to get the P0, it's just the A, or you could do this algebra. The cheating way to get the K that I need is just going to be the natural log of what my calculator calls B. My calculator called B 0.986, so this is going to be the natural log of 0.986, because 0.986 is the B. If I take the natural log of 0.986, I get the K is negative 0.014. So the formula, the appropriate regression equation, exponential regression, the answer for part 2C, the equation that I could use to make predictions about the engine temperature is P of T equals 231.384 times E to the negative 0.014 T. To show you how to get the value of K, not doing the cheating way, it's similar to this. Let me show you real quickly how to get the value of K with algebra. So if I wanted to find the K and I didn't want to cheat, I know I have my calculator equation is 231.384 times 0.986 to the T, and I know my equation is going to be 231.384 times e to the kt. I'm going to divide both sides by 231.384. When I do that, I get 0.986 to the t equals e to the kt. And the slick thing to do is to let t equal to 1. Again, this doesn't feel legal unless you've done this a bunch of times and figure out that it is something legal to do. For this statement to be true, it needs to be true for all values of t, must be true for t equal to 1. So if I get 0.986 to the 1 equals e to the k times 1, that leaves me 0.986 equals e to the k. I'm going to take the natural log of both sides. Get the natural log of 0.986 equals the natural log of e to the k. This gives me the natural log of 0.986 equals k times the natural log of e. The natural log of e is 1, so I get the natural log of 0.986 equals to k, and that's what my shortcut says. Just take the natural log of b and you'll get the value of k. So for each of the first few problems that I do, at some point we're going to be asked to find an appropriate regression equation, and for the exponential regression that my calculator does, it doesn't give the formula in such a nice form, and will transform that formula, or equation that my calculator gives me, by using the fact that a is going to be p naught and k is going to be the natural log of b. So immediately when my calculator gives me an exponential regression, I'm going to make the a equal to p naught, and I'm going to make the k equal to the natural log of b. And then I'll take the calculator's equation and make it into an equation that I can use to solve the problems that I want to solve. So the whole work for problem 2C is to come up with an equation, and let me pretend that I've just started. So if I just was visiting 2C and it said find the appropriate regression equation. So if this was a new problem, I'd do the exponential regression on my calculator, and my calculator would say, it says that y, well, it doesn't even say it. Well, I won't see it anymore. When I do it on my calculator, it says stat calc exponential regression, enter, enter. It says y equals a times b to the x, and then specifically it says a equals 231.384 and b equals 0.986. My desired equation is of the form p of t equals p sub 0 times e to the kt. P sub 0 is just going to be the a, so my desired equation is going to be 231.384 times e, and the k is going to be the natural log of b. So the k is going to be the natural log of 0.986, which apparently is negative 0.014. So the equation that I'm going to use to answer questions about the engine temperature is P of t equals 231.384 times e to the negative 0.014 t. That's taking the values that my calculator gives me when I do exponential regression, making the p naught p sub 0 equal to a, and making the k the natural log of b. This is the equation I'm going to use to answer the question in part 2D. The question in 2D says predict when the temperature will be 140 degrees Fahrenheit. So the function that I have to work with will predict the temperature at any time in minutes, because the time intervals were in minutes. What I'm going to do, I'm not going to put 140 in for the t, because 140 is a temperature, not a time, and this t stands for the time in minutes. I'm going to put 140 on the left-hand side of the equation for the temperature function, and I'm going to solve for the t, and that's going to be time in minutes. To solve this, it's going to get a little bit messy. I'm going to start off by dividing both sides by 231.384, and the harsher I round the left side, the less accurate my answer is going to be. I'm just going to round the left side to 3 decimals. And I'm going to go on the left side, I'm going to go 140 divided by 231.384, and I'm going to get 0.605. Hopefully you could see that on my calculator. I'll flash it back up here just in case you couldn't. So doing that computation, 140 divided by 231.384 gives me 0.605 on the left side. It cancels the 231 on the right side and just leaves me the e piece. Now I'm going to take the natural log of both sides. Get the natural log of 0.605 equals the natural log of e to the negative 0.014t. This is going to give me the natural log of 0.605 equals, use the exponent to multiplication rule, equals negative 0.014t times the natural log of e. Just like we've done a bunch of times now, the natural log of e is 1. So I get the natural log of 0.605 equals negative 0.014t. To solve for t, I'm going to divide both sides by negative 0.014. And when I do that, the right side's going to give me the t, which is the time in minutes. The left side's going to give me my answer. It doesn't say, I could round to the nearest minute, but usually I round to 2 decimals for my answer, so I'm going to round to 2 decimals, even though it doesn't say where to round. So I'm going to go the natural log of 0.605 divided by negative 0.014. That's more or less readable. It gives me a time in minutes. I'm going to write 35.89 minutes according to this formula for the engine temperature to be 140 degrees Fahrenheit. And my answer is just going to be 35.89 minutes. If you rounded to 36 minutes because I didn't say where to round, then I'd have to take credit for that. Similarly, if you gave me more than 2 decimals because I didn't take the time to say this is where how you need to round, then I'd take another answer as well. 4 is going to be another exponential regression. This is actually an exponential growth as opposed to decay. And so again, as I read, this problem is set up similarly. It gives me a table. It says this particular table gives me the number of computers infected with a virus after so many days. So the time is going to be in days. What I get is the number of computers infected. So after the first day, there were 10 computers infected, the second 39, the third 82, and so forth. I plotted the data, and you can see this big curve in here. This is your classic exponential growth look. The type of function that's going to be, again, appropriate is exponential regression. But let me get this set up on my calculator real quick so I can get the equation that I need in a minute. So I'm going to clear this out. I hit my stat button. I hit enter on edit. I arrow up to the top of list 2, hit clear and clear that out. Go up to the top of list 1, hit clear and clear that list out. Now I'm going to enter the days or the times in list 1. So I enter the numbers 1 through 6 in list 1. And in list 2, I enter the number of computers infected. And so now I have the data in more or less correct. If I hit second and quit, and then zoom stat, go to number 9, it's going to plot the data for me. And that plot looks a lot like my plot. That's definitely not a line. And that kind of just looks like our classic 2 to the x or 3 to the x or e to the x graph. So this is definitely something that exponential regression is going to be appropriate. When we get to the test, and I believe on the review, the one question that comes from this section, it doesn't even ask the part A and part B. It gives you a table of data, and it asks basically the part C and the part D. So I won't have you plot a graph or decide the appropriate type of equation. It forces your hand. It says use exponential regression and create an equation with the P form. So now I'm going to get to the second part of this, which is the test-worthy part. Specifically, I'm going to come up with an equation and write it in the right form using exponential regression. Immediately, I'm going to use my calculator, and it's going to give me an equation in the form a times b to the x. For my formula, whatever the a is, that's what I'm going to put in for p sub 0. And for the k, I'm going to put the natural log of b. So once I get to my calculator and do the regression, my answer to part C is going to be an equation. P of t equals something times e to the k t power. I need a value for p sub 0, which is going to be the a. I need a value for k, which is going to be the natural log of b. So now I'm going to hit stat, go over to calc, go down to exponential regression, which is option 10 or option 0 it looks like. Hit enter twice, and I'm told that the a in the equation from my calculator is 6.244, and that the b is 2.21, and I'm going to round to 3 decimals. Since it's 2155, I'm going to write 2.216. The equation that I'm going to have, this 6.244, I get a little out of control with my 4s. That 6.244 is going to go in from my p sub 0, and it's going to be to the left of the e. The k is going to be the natural log of this 2.216, and again I'm going to carry 3 decimals worth of accuracy. So to get the k for my formula, I hit my natural log button, type 2.216, close out my parentheses, and I get 0.79, and I'm going to round that to 0.796. It's 0.7957, and I'm going to round the 5 up to a 6 and write 0.796 6t. So that says P of t equals 6.244 times e to the 0.796t. That's the equation that I'm going to use to answer questions about the number of computers infected with some sort of virus. So that's the answer to part C. I'm going to need this equation when I do part D. So in part D, I'm using the equation P of t equals 6.244 times e to the 0.796t. I need to predict when 1 million computers are going to be infected, and that means I'm going to have to change the left-hand side to 1 million. And this virus is spreading really fast. After 6 days, there were only 656 computers infected. It's not going to take that long for 656 computers to grow to 1 million computers because of how steeply, how quickly the graph is growing. Because this graph is shooting way up like this so quickly, it's not going to take that long before the y is up to 1 million. That's what I'm going to find out. The algebra I'm going to do is going to get a value for t, which is the number of days it's going to take for the number of computers infected to be 1 million. What I'm going to do is I'm going to change the p of t, the number of computers infected, to 1 million, and I'm going to solve for t. To do this, I'm going to divide both sides by 6.244. On the left-hand side, I'm going to round to 3 decimals. So I'm going to go 1 million divide it by 6.244, and I get 160,153.74. I'm going to round that to 8, so I'm going to say 160,153.748 equals e to the 0.796 t. I'm going to take the natural log of both sides. So natural log of this side, natural log of that side. On the left-hand side, it's still the natural log of 160,000. I get the natural log of 160,153.748. On the right-hand side, I make the 0.796 the coefficient. So it's 0.796 times the natural log of e. The natural log of e is equal to 1. So I can get the natural log of 160,153.748 equals 0.796 t. T is what I'm looking for. It's the time in days that it takes 1 million computers to be infected. I'm going to divide both sides by 0.796. The right side I don't need my calculator for. That's going to be the number of days. This I do need my calculator for. So I'm going to go the natural log of 160,153.748, close my parentheses, divide it by 0.796, and my calculator is going to tell me that it's going to be 15.055 days. And I didn't say how to round, so 15.055. I've been rounding to 2 decimals. Since I didn't say how to round, again, I couldn't give you any slack for not rounding like I rounded. I should probably go through and change my instructions to tell you how to round, but I didn't. So 15 days, 15.06 days, 15.055 days. I'd live with any of those at this point. Looking for this algebra, then the rounding here is just, it's not, it's nice to round like I did, but it hardly matters. When I plotted the data for 6, it looks so linear that it seems like a line would be appropriate. I'm going to plot this data using our calculator, talk about the data, why it's not linear. So it says a chemist has a 1,000-gram sample of a radioactive material. He records the amount of radioactive material every week for 6 weeks. So this radioactive material starts off with 1,000 grams, but it's unstable. It's decaying, giving off radiation and probably doing bad things to the scientist. But it says from the initial amount of 1,000 grams, after 6 weeks, it's down to 783 grams. It says take this data and graph it. Easy enough to do. Hit my stat button, hit enter on edit, clear out the list 2, clear out the list 1. In list 1, I'm going to put the numbers 0, 1, 2, 3, 4, 5, and 6, which are the weeks. In list 2, 1,000 grams, 960 grams, 922 grams, 885 grams, 850 grams, 815 grams, 783 grams. Second, quit, do zoom stat, and boy, that does look linear. It looks so perfectly linear. For it to be exactly linear, every one of the differences, the difference between 1,000 and 960 is 40. The difference between 960 and 922 is 38. The difference between 922 and 885 is 37. The difference between 885 and 850 is 35. The difference between 850 and 815 is 35. Because the number, the gap between the weights isn't constant because it's decreasing, a line isn't the most appropriate. But if you said linear regression, because when you hit zoom stat it looks like a line, I definitely couldn't fault you for that, because that looks linear to me. I don't even see the curve in this data that I need to be. But there is supposed to be a slight curve to this data, and this is supposed to be something that could be modeled by exponential decay. And again, on the test, as well as on the review, the question that comes from this section doesn't have the part 6a and 6b. I just tell you, use exponential regression, so you won't even have to worry about, well, what if I used linear regression? How well would that be usable to predict this? I imagine that if we did linear regression, that over a short number of days, short number of weeks, maybe up to 10 weeks, that it would be almost as accurate as the exponential regression. But once we start getting further down the line, this data is going to get more. It's going to get less linear and it's going to get more curved. And at some point, the line's going to not be a good predictor. Again, if you wrote linear regression here, I'd completely say that's okay, because that definitely looks linear. Not an issue, because on the test you won't be asked to graph the data, you won't be asked to decide what regression model is appropriate. You're going to be asked to create an exponential regression model and use that exponential regression model to answer questions. So I'm going to do exponential regression, EXP REG on my calculator. It's going to give me y equals a to the b times x. My goal is to come up with an equation in the form p of t equals p sub 0 times e to the kt. And again, I'm going to cheat. I'm going to say that p sub 0 is going to be the same as a, and that k is going to be the natural log of b. Rather than going through the algebra to actually find how to get that, I use the shortcut strategy. So now that I know what I'm shooting for, I'm told you here, basically here I told you that I want you to use the exponential regression when I give you an equation that's an exponential equation. So I'm going to hit my stat button, go over to calc, go down or up and find number 10, EXP regression, hit enter twice, and it tells me that the A, again I'm going to round to 3 decimals just so I'm consistent with myself, is 1,000.156, and it says the B is 0.960. When I go to write my equation, I don't know if you can see that, when I go to write my equation, I'm going to put, for the P's of 0, for the initial quantity, I'm going to put 1,000.156. We know there was only 1,000 grams. This is slightly over 1,000 grams, but it's okay. And then for the K, I'm going to put the natural log of B. I'm going to do the natural log of 0.960, and I get negative 0.0408, so I'm going to round that to negative 0.041. I'm going to put those two values into the formula, and that's going to be my answer for 6C. So for 6C, the exponential equation that's going to use to model this data is 1,000.156 times e to the negative 0.041 t power. So that's the answer to part 6C. That's something you're going to be required to do on the test. Similarly, you're going to be required to do something like 6D. When I go to do 6D, predict when 500 grams of the material will be left, I'll use the equation I developed in 6C, and I'll take that 500 and put it in the appropriate place. It doesn't go in for the T because T stands for time, and that 500 grams is not time, it's the amount of material. So I'm going to plug 500 in for the P of T, and I'm going to solve for the time. And I believe this is going to be time in weeks, because the data that's given to me, when I read the data, it said the amount of radioactive material present every week for 6 weeks is given in this table, so the time is going to be in weeks. To do this, I'm going to solve it by dividing both sides by 100.156, 1,000.156. I'm going to carry 3 decimals. So on the left-hand side, when I do my division of 500 divided by 1,000.156, I get 0.4999. That's going to round to 0.50 because the 9 in the third position. So this, I have 0.4999 for the number that my calculator gave me. And again, I never know how well you can see that. This 9 in the fourth position is going to round that 9 up to a 10, which is going to round that 9 up to a 10, which is going to round that 4 up to a 5. I can write 0.5, or I can have the 2 zeros. It doesn't matter. If I do, I don't include the zeros after the 0.5. The right-hand side, I've canceled out the thousands. Now I'm going to take the natural log of both sides. Leave the left side the natural log of 0.500. On the right side, make the exponent into a coefficient. So I get the natural log of 0.5 equals negative 0.041 times the natural log of e. the natural log of e is equal to 1, so I get the natural log of 0.500 equals negative 0.041 t. I'm going to divide both sides by negative 0.041. Left side is my calculator. The right side gives me the time. Left side, I'm going to tack the word weeks onto my time because it's time in weeks. And again, that's just natural log of 0.5. I don't really need the 0 zeros. Divided by negative 0.041. And when I do that, I get 16.906 weeks, so almost 17 weeks. Hopefully you can actually see that. So the answer to part D is 16.906 weeks. If you had the desire to stop the video now, this is the only thing from this section that's test worthy. I have one more problem I'm going to do because I'm supposed to cover it, but it's not anything that you're going to see for the rest of this class. I don't think you see it in brief calculus or regular calculus, so I don't feel that tied to making you watch it. So if you stopped the video now and only went up to problem 6 on the homework, you'll be fine. If you want to go further, then we can do this problem 8. And the difference between problem 8 and the first group of problems is it's not an exponential function that's appropriate, because the data, it has a curve that kind of bends down like this. Exponential functions either have curves that look like that or look like that. This particular data, when I get it plotted, it doesn't look like exponential decay, which this is a kind of the look of exponential decay. This is exponential growth, and it doesn't have the look of either one of these. This actually looks like the graph of a logarithmic, and when I get into this, the appropriate model for this is going to be logarithmic regression. So there's only one problem like this in section 6-9 because I'm told to cover it. So I just wanted to expose you to it just so you are aware that there are many, many types of regression. We did linear regression and quadratic regression earlier this semester, and we've done exponential regression in this section. If you just hit your stat button and go to calc, look at all, we have linear regression, quadratic regression, cubic regression, quartic regression, linear regression, again, written 2 different ways. I think one's for business people, one for scientists. LN regression, that's the logarithmic regression that we're going to do next. That's natural log regression. Exponential regression, power regression we haven't talked about, logistic regression we haven't talked about, sign regression, manual fit we're not going to do. So there's lots of regressions even just on the TI-84 calculator, which is just a fraction of the regressions that are available in the real world. So regression is a huge deal. I just read an article on Yahoo News yesterday that I almost displayed, but I'm like, no, who wants to read that? But basically it talked about biologists, and biologists really have the need to be able to do regression because biologists collect gobs of data, and if they want to make any predictions with their data, they have to do some sort of regression so that they can make mathematically significant predictions about their data. But a lot of biologists are deficient in their math, and that's kind of slowing the whole field of whatever studying that they're doing down because their lack of mathematical abilities. Anyways, for this problem, I'm going to enter the data in. The first data I'm going to enter in list 1. That's the age of some trees, these mesquite trees, and the next data is the height of the trees after years. So the time is in years. So I'm going to go edit, clear out the list 2, clear out the list 1. In list 1, I'm putting the years from 1 year to 10 years. And in list 2, I'm doing the height of the tree, 4 feet, 7.5 feet, 10 feet. I made these numbers up. I'm not sure exactly how tall Chilean mesquite trees get, but this goes up to 17.9 feet. I've already I can tell I made a mistake because my lists don't pair up. And what happened is I typed 56 instead of 5, then 6. So you have to have the data entered in properly. If the data is not entered in right, then your calculator is hopeless. Now I'm going to hit zoom stat just to graph and show you that the graph should be something like, and look at this, I have this funky point here. It tells me I entered a point wrong. Let me check my stat, edit. 2, I wrote 0.75. I was supposed to put 7.5. I'm glad that I took the time to actually graph that because now it looks better. So the graphing would have made me worry that I messed up. So this is the logarithmic or natural log regression would be very appropriate here because this is how a logarithm graph looks. We graphed quite a few logarithm equations. So this would be logarithmic equation regression. The nice thing about logarithmic regression, the equation that my calculator gives me it doesn't need to be tweaked. So when I go to come up with the appropriate regression equation, I said the equation your calculator generates will not need to be changed. So I just need to, well, I might need to change an x to a t to stand for time, but other than that. So I'm going to go stat, calc, go down to ln regression, natural log regression, hit enter twice. My calculator tells me that the equation is in the form y equals a plus b times the natural log of x. And it tells me that A is 3.525 and that B is 6.581. And then it gives me the correlation, the R numbers, and you can see that's a really good fit. Anytime you get these over 0.8, you're doing well. So I'm going to plug those numbers in, and that's going to be the answer to part 8C. So in some sense, it's way easier than the last group of problems because I don't need to put it, the form that it gives it to me is the standard form, other than I'm going to change the x to a t because I'm dealing with time and x doesn't look like time. So this would be the appropriate equation for 8C to model the growth of those mesquite trees. Last thing I need to do is predict when the trees are going to be 19 feet high. I'm going to use the equation y equals 3.525 plus 6.581 times the natural log of t. I'm going to put 19 in for the y, which is the height. I guess I could have used some sort of function symbol here, but I didn't feel the need. So I'm going to get 19 for the height, which stands for the y's, equals 3.525 plus 6.581 times the natural log of t. Take a few steps to solve this. The first thing I'm going to do is subtract 3.525 from each side. I'm going to use my calculator on the left side. I'm going 19 minus 3.525. I don't care to try to do that in my head. When I do that subtraction, I get 15.475 equals 6.581 times the natural log of t. I'm going to divide both sides by 6.581. And I'm going to carry 3 decimals because that's what I've been carrying for every problem. So I'm going to go 15.475. I'm doing that off screen, but I'm just dividing 15.475 divided by 6.581. I just did that division on my calculator. My calculator gives me 2.351 equals the natural log of t. So just if you want to see my last 2 computations, I did 19 minus 3.525 and got 15.475. And then I did 15.475, which stands for the answer, divided by 6.581 to get the 2.351 figure. I'm almost ready to have this solved, but it's not solvable by hand, written in with the shorthand notation. And I know that ln and log base e are interchangeable. I'm going to write this in log base e form. Now I'm going to get rid of the logarithm. I'm going to cross out the logarithm. The e is going to stay low, and I'm going to switch the 2.351 and the t. So whatever e to the 2.351 power is going to be the time that it takes these trees to get to 19 feet, and it's going to be in years. So I'm going to go second ln 2.351 power, and I get 10.4. Now, how cruddy is that? Really? 10.49 years. Does that even fit my data? Seems to me. Maybe it does. Oh, I guess it, no. Yeah, I guess. it's not that wacky. At 10 years, they're almost at 18 feet. My formula says at 10 and a half years, they're going to be at 20 feet. That's probably a little aggressive. Probably in reality, they're not growing that fast anymore after 10 years. It might take a little bit longer than that. But again, when you're using mathematical models to make predictions, they only do so well. And we're dealing with really small data sets. If I had like 1,000 points of data, and I did the regression, it would be way more accurate than making regressions with 5, 6, and 8 points. That's just not enough points to make really good predictions. Somehow 30 is a magic number in statistics. I imagine having 30 data points, we'd get a much more accurate equation, an equation that's better to use for prediction. But I don't have the desire to enter 30 points or 50 points or 100 points to find my equations. And this kind of just gives you the idea of what mathematicians or scientists do without making it so realistic that it's just a nuisance to do. I guess if I was going to do this sort of regression with real data in large quantities, I'd use a computer rather than my calculator. So that's the end of this section. Again, the last problem on the logarithmic or the natural log regression won't be on the test. You're only responsible kind of for the problems up to problem 6 in section 6.9. And you should definitely be able to tell that that does not even spell close to right, is it? Exponential regression. Sorry about that horrible spelling. That's why I'm in here teaching math, I guess. Hopefully I didn't continue to spell that so horribly. Who knows? Spelled exponent. It's still not spelled right. My gosh. And I'm videotaping these. Oh well. So hopefully nobody that pays me watches this and sees that I can't spell. So hopefully this went reasonably well and that the test isn't nightmarish. There's a lot of overlap between this chapter that we just did and the chapter in intermediate algebra. So hopefully getting this a second time through has made you a little bit better with logarithms and exponential functions, because they come up a ton, especially in brief calculus. They're just way overloaded with these functions in Math 212. So if you're going that direction, you're going to get really good with these. Not as much in Math 220. They come up, but they're not as predominant as they are in Math 212. Alrighty.